Let's integrate x squared from 0 to 1 by using the definition of integral. Now, since the function x squared is continuous, it's integrable. So it won't matter exactly how we choose our partition or how we choose our sample points, as long as the partition is fine enough. So I'm going to choose a partition where each of the subintervals has the same width, 1 over n. I'm going to divide the interval into n pieces, each with the same size. Now I got to figure out exactly where those cut points are being made, and I'm labeling those points x sub I. So my left-hand endpoint is x sub 0, and my right-hand endpoint is x sub n. And my cut points in between, where I'm cutting up to partition, are at I over n. So the first one here, or the one after the 0th one anyway, is 1 over n. The next one is 2 over n. The next one's 3 over n. And each of those subintervals has the same width, 1 over n. Now I also have to choose points to sample the function at, and I'm just going to choose the right-hand endpoint here. So my x sub 1 sample point will be 1 over n, my x sub 2 sample point will be 2 over n, and so on. And now I can write down the Riemann sum. Right? The Riemann sum is the sum. I goes from 1 to n, the function evaluated at the sample point times the width of this ith interval, right, which I could write as x sub I minus x sub I minus 1. Now in this case, some of this is a little bit easier. I can write this a little bit more nicely, right? F of x sub I star being I over n, and the function being the squaring function, I can rewrite this Riemann sum as I over n squared. And then x sub I minus x sub I minus 1, that's just the width of the ith subinterval in my partition, and that's, how far apart these numbers are, and that's 1 over n. So there is my Riemann sum associated to this particular partition and my particular choice of sample point. I can evaluate that exactly by using some of the facts we've learned about sums. In fact, we want to do a little bit more than just evaluate this, right? I want to take the limit of this as n goes to infinity, and by choosing finer and finer partitions, that's going to give me better and better approximations to the true area under the graph of this function, right? That's the area that I'm trying to calculate by evaluating this particular Riemann sum and taking the limit as the number of pieces in my equal length partition goes to infinity. Okay, so this is really what I want to calculate. All right, I want to calculate the limit as the number of things in my partition, each of equal size, goes to infinity, right? That's a finer and finer partition, and this is the Riemann sum that we had before, and this is calculating the integral from 0 to 1 of x squared. All right, well, how do I do this now? Well, this is the limit as n approaches infinity of the sum. I goes from 1 to n, and this is I squared over n squared times 1 over n. Now n is a constant, so I can pull this out of the sum by using distributivity. This is the limit as n approaches infinity of 1 over n cubed times the sum of I squared. I goes from 1 to n. Now we think back, I've got a formula for the sum of the first n perfect squares, right? That formula tells me that this is the limit as n goes to infinity of 1 over n cubed times, and what's the sum of the first n perfect squares? It's n times n plus 1 times 2n plus 1 all over 6. Now I could expand that out. This is the limit as n goes to infinity of 1 over n cubed times 2n cubed plus 3n squared plus n all over 6. And this limit, well, it really just matters, right, what these highest powers are. There's an n cubed in the denominator, or really a 6n cubed in the denominator, and a 2n cubed in the numerator. And as n approaches infinity, this is 1/3. Let's summarize this with an official-looking statement. So the integral from 0 to 1 of x squared dx, right, we just calculated this is 1/3. And what that's really saying is that if I've got, say, this graph here, say this is the graph of y equals x squared, this integral is calculating this area, right? The area between 0 and 1 underneath the graph of x squared, right? This red area here is 1/3 square unit as a result of the integral calculation. Now I can play around with this a little bit. So to say that the integral from 0 to 1 of x squared dx is 1/3, well, one thing I could do with this is I could multiply this by 3, right? What's 3 times the integral from 0 to 1 of x squared? Well, that's 3 times 1/3, that's equal to 1. But 3 times an integral, that's the same as integrating from 0 to 1 3 times the function, right? This is really worth thinking about. I mean, here I'm taking this area and multiplying it by 3. Here I'm calculating the area of the graph stretched in the y direction by 3 times, right? And these are the same. And this is saying that the integral from 0 to 1 of 3x squared dx is equal to 1. So what does that mean? So here I've graphed the function y equals x squared from 0 to 1, and the area in there is 1/3 of a square unit. That's the first calculation that we did. And now what I'm claiming is that if I took the same function here but multiplied it by 3, right, which has the effect of stretching it just in the y direction by 3 times as much, well, that triples the area. So the original area here was 1/3, but now this new area is 1 square unit, right, which is what I've written here. Okay, so what does it mean to say that the area under the graph is 1 square unit? Well, what I don't mean is that I can take a square of side length 1 and cut it up and exactly cover that region. That's really not what I'm talking about when I claim that that region has area 1. If I claim that that region has area 1, I really mean two different things. I mean that if I had a square with just the little tiny corner nicked off of it, I could take that thing that has area just under 1 unit and chop it up into little pieces and fit that thing entirely inside my curved region. Conversely, I mean that I could take a square of side length 1 and just a little bit of extra area, and I could cut that thing up into little tiny pieces and cover up my curved region, right? But it's fundamentally all about limits, right? This whole story isn't actually about achieving anything. It's just saying that I can get as close as I want, right? It's saying that I can take this almost 1 square unit and fit it entirely inside. Or I could take just a little bit more than 1 square unit and cover it up. But I'm never actually asserting that things are equal. I'm just saying that they're as close as I'd like them to be.